I see the time is 1:35, so let's start the class for today. Let's wrap up the secondary electron part. Last week, we discussed how secondary electrons are generated, as well as what conditions we can tune, we can play with to change the yield of secondary electrons. We mainly focused on two things. We focused on the beam energy, as well as the atomic number. I hope you still remember, by changing the beam energy, by changing the acceleration voltage for the electron beam, we can change the yield. But in contrast, the atomic number of your sample is insensitive. Like the yield of secondary electrons, it's insensitive to the atomic number of your sample. We also slightly talked about the charging issue on insulating non-conducting materials. The last bit I want to talk about is the effect of band gap on secondary electron yield. I know many of the, I wouldn't say many, some of the students are interested in working in semiconductor industry. So we'll see how we can use secondary electrons to roughly tell or to distinguish materials or similar materials of different band gap energies. Let's assume we have silicon. So we have silicon here, but locally, the region here, we dope, for example, with germanium. By doping germanium into silicon, it will narrow the band gap. So let's just draw the band diagram. We have the conduction band. So let's call CB. That's the conduction band. Then in the silicon part, the valence band is down here. That's for silicon. Then for the silicon doped with germanium, the valence band is elevated. I'm exaggerating that here. Then the band gap is smaller. Let me ask you, like, which one will yield more secondary electrons, silicon or germanium doped silicon? If you have any guesses, would you like to speak up? So there will be secondary electrons generated. Take a guess, which one will generate more secondary electrons?
Isn't it the same?
There's a slight difference. There's a slight difference. By the way, the effect of band gap on the secondary electron yield is not huge, but in some of the cases, you can still see the difference.
The one with germanium?
Yes, yes, excellent. So the one with germanium, doped with germanium, will yield more secondary electrons. Why? Would you like to give a try?
It's narrower space, so there's less barrier to overcome to reach to the get to the conduction band.
Excellent, excellent. So the band gap is smaller. So the electrons are more loosely bonded to the nuclei in the material. So it's easier to knock out these electrons. So if you have a semiconductor, which one has smaller, like if you have a component having smaller band gap, then that part will yield more secondary electrons. Does this make sense? Okay.
Excuse me, what is VB?
Valence band. Sorry, let me write them out for you. So this is valence band. And CB is conduction band. If you have similar materials or very similar materials, one has a large band gap, another one has a small band gap, then the one with smaller band gap will be willing to give out more electrons because the electrons are more loosely bonded. Any other questions before we move on? Okay. Okay, that's everything about secondary electrons. The second major type of information you can acquire by having the interactions of electron beam and material is the backscattered electrons. So that's the second type of signals we can generate. So in abbreviation, it's called BSE. Let me ask you something very simple. For BSE, are they primary electrons or secondary electrons?
Primary electron.
Primary. Okay, excellent. So the backscattered electrons, those are primary electrons. So those are the electrons from the electron source, from the electron guns. While the secondary electrons are from the material. It's kind of like you go to a restaurant, you pay money, then the secondary electrons is kind of you're getting change. So the money is not from you. Then the primary electrons is like you go to the restaurant, you pay for the bill, they give some of the money back to you. So that's the difference. So it's, those are primary electrons. Let's draw one atomic model. Assuming this is the nucleus. And we have the electron orbitals around it. In the first case, let's call it low Z. And in the second case, let me draw a bigger nucleus, put a lot more charges in it. Okay. And we have the electron orbitals. When we have the incident electron coming in, if it's low Z, when the electron travels very close to the nucleus, it will be attracted. Then it will be swung back. But the angle is fairly, let me think about how to describe it. Should I say small or large? Like it's coming back. But in the high Z case, when we have the incoming electron, because the Coulombic force is so strong, it will be able to swing it kind of all the way back. So that's the difference. That's the difference when we have a low Z material and when we have a high Z material. Now, looking at the yield of the backscattered electrons, similar to what we did with the secondary electrons, let's look at two things, the effect of voltage and the effect of Z. Let's start by looking at the effect of the beam energy. On the x-axis, that's KeV, that's the acceleration voltage. On the y-axis, that's the yield, that's eta. What people found was it's a straight line. Doesn't matter how you change the KeV, the yield of backscattered electrons is relatively insensitive to that. So this is in contrast to what we discussed back in the secondary electrons. Now, let's look at the effect of Z. The atomic number of your specimen. From the previous schematic, you can kind of tell that already. So on the x-axis, that is Z, the atomic number of your sample. Then on the y axis, that's again eta, that's the yield, then you'll see something like this. As Z increases, we get more backscattered electrons. We can also look at the ratio using two examples. For people who work on metals, you are probably familiar with aluminum and tungsten. Aluminum is low Z. So let's just say low Z. The yield is about 0.15. That means when you throw in 100 primary electrons, 15 electrons will come back as backscattered electrons. For tungsten, eta is about 0.5. So tungsten is very heavy, so it's high Z. And also it's at the bottom of the periodic table. For tungsten, every 100 electrons you throw in the material, half of them will swing back. So those are just two examples. Then you may wonder, what is the primary use of BSE? The primary use of BSE is to study the second phases and the precipitates in metals and ceramics. So let me write that down for you. In most metals and ceramic systems, the second phases and the precipitates, they usually are made of different elements. So the Z of precipitates and the second phases, they are different from those in the matrix. So because of the difference in Z, you're able to tell them apart straight away. So this is the main use of BSE. Because BSE, the backscattered electrons, when they are generated, they just swing backwards. We need a dedicated detector for that. In the lab last week, you've seen that already. We have to manually insert an additional detector. So this is called the BSE detector. So we need a dedicated BSE detector. If we draw the schematic of SEM again, okay, if the secondary electron detector is here, so this is the SE detector. Then we have the BSE detector like this. That's what we inserted into the microscope in the lab demo session. We have the sample here. So that's the specimen. We have the electron beam coming there from the source, hitting the specimen. Then the secondary electrons, they kind of fly in all different directions, but the bias on the grid will attract the secondary electrons. So the magenta lines, those are SE secondary electrons captured by the secondary electron detector. And the backscattered electrons, remember they backscatter, they swing back. They are captured by the BSE detector. Does this make sense? Any questions? So for
I have a quick question about the bias. Is that something that we can manipulate, or is it just standard for the setup?
That's a good question. That's something we cannot manipulate. It's the setup by the detector company.
Got it. Thank you.
Okay, cool. One thing I forgot to tell you, by the way, like the BSE detector, what we drew here, what we sketched here, that's the side view. If we look at from the top, let's just draw that again. It's more like a disk. So let me say this is top view, top view. When we take a slice, it looks like just two chunks here, but from the top, it's really like something annulus. And that's how the BSE detectors are captured. Another thing is, like one thing I like to draw attention to is, if you look at BSE, not all electrons, they are going like straight back. Some of them, they may have larger angle, can I say that? Like, you know, they deviate from the way they're supposed to. Then some BSE, like over a few BSE electrons will hit the secondary electron detector. So when you use secondary electron detector to do imaging, please be aware, you always pick up some or small amount of BSE. So let's just write it. So note, you always pick up small amount of BSE in the SE detector. If you recall what we saw in the lab last week, we used magnesium alloy as a model material. And in the magnesium alloy, we have precipitates. In the backscattered image, the precipitates, they just light up. They just light up. It's so clear to see. But when we had a closer look at the secondary electron images, we see some faint contrast as well. The reason for that is because some BSE can always reach the SE detector. So when we use an SE detector, what we get is largely secondary electron information and a very, very, very small amount of BSE information. That's something I hope you'll be aware of. We'll have another look at the same sample today and go deeper in that direction. Any questions about BSE, like the regular BSE? Before we do the energy comparison of secondary electrons and the BSE electrons.
So I have a quick question. Why are not all backscattered electrons are not collected by SE detector, since there is a positive voltage there in the mesh?
That's an excellent question. That's something I'm going to cover next, but I'll give you the answer now. The reason is because from the last class, we learned the primary electron, the energy is very high. It's very high. It's keV. It's kilo electron volts. But secondary electrons, the energy are much lower. They are in the orders of few EVs or tens of EVs. So there's a huge difference in energy. For secondary electron detector, if you apply a small bias on the grid, then the low energy SE will be attracted to the SE detector, but the high energy BSE, their path will be slightly deviated, but not by much. Does this answer your question?
Yes, thank you.
Okay, that's an excellent question. That's an excellent question. Any other questions before we compare the yield and energy of SE and BSE? Okay, if not, let's do the quick comparison. So SE versus BSE? We'll look at two things. That's yield and energy. What we can do is just to draw one graph. To capture both information. So on the x-axis, that's the energy. So we can say EV. On the y-axis, that's the yield or number of electrons. When we have electron beam interacting with the samples, we generate secondary electrons and the BSE. So this is 0, and this is the beam energy. So for SE, we get a huge amount of that, but the energy is very low. It quickly drops. And we have some noise. And at where we are getting close to the beam energy, we have another hump. So this is SE. This is BSE. Let's look at why, in terms of numbers and energies, there's a difference. In SE, if you recall from what we discussed last week, when you throw in one SE, there are multiple, when you throw in one primary electron into the material, there are multiple secondary electrons generated. So the yield for SE is high, but for BSE, when we throw in one primary electron, even for something as heavy as tungsten, only half an atom can come out. That's why, in terms of numbers, there is a huge difference. And that's why, in the same condition, you may see a very clear and not noisy, very clear, very good signal to noise ratio image from SE, but very noisy BSE image. This is in terms of the number of electrons we're getting. Then in terms of the energy, SE is much lower, then BSE is much higher. The reason is because for SE, those are electrons bonded by the nuclei in the material. If we think about the energy, it's in terms of EV range. So that's the range of the energy. But for BSE, it's very close to, first of all, it's the primary electron. Even after losing some energy, in terms of energy, it's very close to the primary electron, to the electron just coming out from the source. Even after, like inelastic scattering, even after losing some energy, it's still more or less the same. So that's why the energy is very high. Does this make sense? In terms of yield and energy, BSE is kind of like you're super, super rich, then you throw away $10, $20. When you come back home, like you are pretty much still as wealthy as you are, more or less. But secondary electrons, they are like 1 cent, 2 cents. They're more like after transaction, after large transaction, those are the change you get. If I use like the money analogy, SE is like you hand me $100 bills, I give you like $1 notes and some pennies. So in terms of numbers, it's a lot, but in terms of energy, it's not a lot. Any questions before we move on? So it's all clear? Okay, good. Okay, we'll look at one last thing before we move to the next section of the class. Nowadays, in the SEMs, the SEM companies, they designed something really fancy called inland detectors. And in the lab today, I'll do a demo on the inland detectors as well. So what is inland detector? Let's just draw the SEM again. Very small schematic. Then we'll zoom in. Remember, we talked about like the lens systems. The first set is the condenser lens. Then after that, we have the scanning coils. And after that, we have the objective lens. Then if we focus kind of here, the piece that holds the objective lens is also called pole piece. So if we focus here, we can draw something like this. And you have your sample here. In the regular SEM, the BSE detector will be inserted here. That's in a regular BSE detector. But the in-lens detector is not a regular BSE detector. So this is the sample. The in-lens detectors are equipped here within the lens. Electrons comes down, then it will generate signals. Only the ones having a large, let me rephrase, only the ones really swing backwards can be captured by the detector. So this is the in-lens detector. If we look at the electron beam material interaction, I hope you remember in the lab we said, doesn't matter how fine you tune the beam, it's really the interaction volume that matters. When we have electron interacting the material, the interaction volume is kind of like this, like a teardrop shape. Let me make the specimen larger. It should be a lot deeper. So this is your specimen. Then what happens in this interaction volume is anywhere in the interaction volume, they can generate electrons. The good thing about using the in-lens detector is it only collects signals coming from here. In this case, you're actually getting an improved spatial resolution. By cutting off signals generated from the areas outside the dashed region. Does this make sense? When we talk about resolution, there are two things we need to think about. The first is how fine we can tune the beam. The second is, can we reduce the beam, electron beam material interaction volume? By reducing the area where the signals are generated, we're actually improving the spatial resolution. So by using the in-lens detector, it can help you with that. But in-lens detector is not equipped on every single instrument. So some of the newer ones, they have it, but most SEMs, they don't have them. On Lyra and the Farah, the two SEMs at MCF, both are equipped with in-lens detectors. The in-lens detectors can be used as SE detector, can be used as BSE. When it's used as SE detector, there will be a bias applied on that to attract the secondary electrons. The BSE detector does not have a bias. Any questions about the in-lens detectors?
So you said that they're located in the lens. So is it like the objective lens, or what lenses are we talking about?
That's a good question. They are located within the objective lens.
Okay, thank you.
Any other questions? Okay, if no questions, let me ask you a question. I've discussed the advantage of using the in-lens detectors. The main advantage is we can get a much better improved spatial resolution. What is the disadvantage? What would be the major disadvantage of using this technique?
The limited intensity?
Exactly, exactly. Since you're cutting off a lot of signals, you're only using a small portion of the total signals generated. So you get less signals. You have poor signal to noise ratio, but poor signal to noise ratio. Excellent, excellent. Again, like I've emphasized that a number of times already, in SEM and in many other branches of studies you do, you will see it's always about compromise. You improve one thing, then something else will go bad. Again, whether to use the in-lens detector or not depends on the application. If resolution is the key for your study, then you probably want to sacrifice the signal to noise ratio. But if you want something really clear, something with good signal to noise ratio, then the in-lens detectors are not your choices, should not be the best choices. Okay, any other questions? If not, let's move to the next chapter of our class. So lecture 6. It's still electron beam material interaction, but it will be part 2. Let's recall how secondary electrons are generated. So we have the nucleus at the center. I'll just draw a few more positive charges, okay? And we have electrons going around the nucleus. From the electron source, we have an electron of very high energy. So this is the electron from E-beam or from the electron source. And we know that already it's a primary electron. And I've got to draw the electrons we have in the material. Okay. Then the generation of the secondary electron is the primary electron. It's of so high energy, it can knock out an electron. So this is the SE. then the primary electron will just keep traveling. What happens here is we are left with a state like this. We still have electrons here. But after knocking out, we're left with a hole here. That's an empty hole here. Because the secondary electron, which used to occupy the spot, now is gone. It's an empty space. This energetically is not stable. So the outer shell electron will jump in to fill the hole. From high school physics, from first year physics, you know the energy of the second electron shell. Go on. Is there a question or? Sorry, is there a question or not? Okay, I assume there's no questions. The electron at the higher energy level will jump down, will jump in to fill the hole. From chemistry, you've probably learned the most inner shell is called K shell. And the second shell is called L shell. From physics, this would be 1s. The next one will be 2s. Then the L shell electrons, they have higher energy than the K shell electrons. So there is an energy imbalance. The excess amount of energy is emitted as X-ray, as a photon. Does this make sense? And also for each element, the energy level of each shell is characteristic. That means each element has its unique fingerprint on the electron shell energies. The energy differences is also characteristic. By looking at the energy of X-ray, we'll be able to tell the chemistry of the material. So let's write that down step by step. I just threw at you with a bunch of information. So let's write that down step by step. So step 1, let's just say K shell electron knocked out. Leaving a hole. Then L shell electron. In this example, it doesn't have to be K and L. It can be anything. It can be like M to K, M to L. Then the L shell electron jumped in to fill the hole. And this causes an energy imbalance. Then the excess energy is released as a photon. And the wavelength is in the range of X-ray. Because the energies of orbitals are characteristic. then delta E is also characteristic, like a fingerprint. From this, we can do chemical analysis. That's how we can tell this is aluminum, this is magnesium, this is iron. Does this make sense? Any questions? So what we just discussed is the third type of signals we can generate. The first type is secondary electrons. The second type is backscattered electrons. The third type is X-ray, when we have the electron beam material interaction. Any questions? Okay, so straight after step 4, what I was saying is for X-ray analysis, for chemical analysis, you cannot just put in the sample in the SEM using EDS, getting the results, and just believe what's going on. There are some factors we need to consider in terms of the generation of X-ray. The 3 things we need to worry about is called ZAF, ZAF on X-ray. Z, as you've known already, this is the atomic number. And what I have drawn here is something very similar to what we did with what we've done with the secondary electrons and the backscattered electrons. On the x-axis, that's the atomic number of your material. On the y-axis, that's eta, the yield of characteristic X-ray. Then as Z increases, eta increases. So that means when you have a heavy element or having a high Z element, such as tungsten, gold, platinum, the X-ray yield will be high. You get a lot of X-ray. But if you have a low Z element, such as carbon, boron, nitrogen, oxygen, the yield will be low. If you have tungsten oxide, assuming it's 1-to-1 ratio, if you just look at the X-ray counts, the tungsten X-ray counts will be a lot more than the oxygen counts. Does this make sense? People can still hear me?
Yes, it does.
Yes.
Okay. Okay, great, cool. Then after that, what I mentioned was the Auger electrons, talking about why for low Z elements we don't get X-ray. Assuming we knock out electrons, where did the energy go if it's not emitted as X-ray? The first reason is because the competition of Auger electrons and the characteristic X-ray. For low Z elements, after knocking out the electron, it leaves a hole. But instead of having the high energy level electrons filling in the hole, the outer shell electrons actually getting ejected. So this energy, instead of it's being used to generate X-ray, the energy is used to kick out additional electrons. And these electrons are called Auger electrons. This is the first reason why for low Z elements, they have low yield of the characteristic X-rays. The second, should I keep going or we should wrap up for today? I see now it's 2:29, now it's 2:30. What I'm going to do is let's wrap up for today's class, and we'll start the lab session pretty soon. Before we wrap up, any questions?
Excuse me, I
about,
didn't understand the last part about Auger electron.
Mm-hmm. Yeah, please.
I couldn't understand.
Oh, okay. Okay, let me describe the process again. So the first part of the process, sorry, I did it in the rush. I apologize for that. For Auger electrons, what happens is the first part of the characteristic X-ray generation is the same. You have the incoming electron. So let me use a different color. You have the incoming electron knocking out an electron from the material, and this is ejected as the secondary electron, and the primary electron just keep going into the material. Then what happens is in low Z elements, the outer shell electrons are loosely bonded because of the small Coulombic force, because the Z is low. So the electron, the most outer shell electrons, they're so loose. So instead of actually, let me put it in this way. I forgot one step. The electron from the outer shell will jump in to fill the hole. Then the energy, instead of the excess amount of energy, instead of being released as X-ray, this energy will be used to kick out one of the outer shell electrons. And this electron is called Auger electron. That's why we don't get as many counts as of X-ray compared to high Z elements. Thank you so much. I realized I forgot one step. The higher level electron has to jump in to fill the hole. Then in this case, we have the excess amount of energy. Then how to spend this excess amount of energy? Instead of getting an X-ray and photon out, the energy is used to kick out the outer shell electron as an Auger electron. The person who discovered as well as really understood this phenomenon is a French scientist called Auger. So this type of electrons are named after him, called Auger electrons. There are a number of Auger electron microscopy, Auger electron microscopes in the United States, but not many. I think maybe not more than 10. That's my impression. It's very useful, but not very easy to use. Auger electrons, they are of so low energy. They are so easily to be absorbed by the material. So you can only study the very, very surface of the specimen. After this, do you have a better understanding of what Auger electron is now?
Yes, thank you.
Okay, nice, excellent. The reason why we brought in Auger electrons is because in low Z elements, we have low X-ray counts. We are trying to understand why we have low counts on the characteristic X-ray. That's the reason. In the next class, at the beginning of the next class, we'll look at A, absorption, and the F, fluorescence as well. So all these will affect what you see in the X-ray spectroscopy, the energy dispersive X-ray spectroscopy, EDS, what you see in SEM. In fact, next week when we do the lab, it will be on EDS. Any other questions before we wrap up today's class?